We just talked about the KVL, which basically said that sum of the voltages around the loop is equal to 0. And we solved an example, and then we generalized that example. Let's see that one more time. And we came up with a very interesting circuit called the voltage divider circuit that basically describes how a voltage source divides its voltage between two resistors. And we saw from that if one resistor is much bigger than the other one, most of the voltage drops across that resistor. So let's move on now to the second law of circuit theory. That one is called Kirchoff's current law, or KCL. So Kirchoff's current law. All right, Kirchoff's current law basically says that if you have a bunch of branches coming into a node, it basically says that some of the currents entering a node is equal to some of the currents that are leaving the node. So if we assume that these are branches where current is flowing in these wires here, and there are different currents flowing in these wires, so you got I1 coming into here, there's I2 entering, there's I3 entering, then I4 is leaving, and I5 is leaving. Essentially, what it says is that sum of all the currents entering is equal to sum of all the currents leaving a node. Which makes sense. If you assume electricity, if you make the analogy, and if these are pipes of water, essentially Kirchoff's current law says that the water is not going to pile up at one corner there, assuming that all of the pipes are open and clean. Then it basically says that if water flows in these pipes, it's going to have to leave at some other pipes. So whatever enters must leave. Nothing accumulates at a point. And the same thing happens in electricity. So if electricity follows from different branches, if it enters a particular node, it will have to leave along some other branches. So some of the currents entering a node is equal to some of the currents leaving a node. So in this particular example, then what we can say is that I1 plus I2 plus I3, these are some of the currents entering the node, is equal to some of the currents leaving the node, which is I4 and I5. So this is a statement of essentially KCL. That's a very simple law, and it's easily acceptable. Although most of these laws are based on Maxwell's equations and other more complicated laws of physics, but anyway, we're not going to worry about that. And so some of the currents entering a node is equal to some of the currents leaving a node. Notice that I can algebraically move these to the other sides. For example, I can say I1 plus I2 is equal to I4 plus I5, and bring I3 to the other side, and we have minus I3. So minus I3, so if a current is negative, it means it's flowing in the other direction. So since the direction, so we can say that I2 is entering, and here I3 is entering. I could also say, change the flow of direction here and say minus I3 is leaving. I3 is entering, minus I3 is leaving. So because we can do that, we can actually state KCL in an alternate form, and this is the form we're going to be using. Another way to state KCL is assuming that we can assign arbitrary directions to the flow of current, we can state KCL as such. Sum of the currents leaving a node is equal to 0. We could have said sum of the currents entering a node is also equal to 0. That's also, so you could say sum of the currents entering a node is equal to 0. So that's, so this is one statement of KCL. So this is another statement of KCL. This is another statement of KCL. All of these are equivalent. In this course, we are going to standardize our KCL using this form. So whenever we would like to state KCL, just by convention, we're going to say sum of the currents leaving a node is equal to 0. So that's how we're going to state our KCL. Again, notice that there's 3 equivalent ways of stating it. Just to avoid confusion, we're going to stick with one form. So the form we're going to pick is the one that says that sum of the currents leaving a node is equal to 0. Again, that's just by convention, and it doesn't really make any difference. So this is KCL. So KVL says that sum of the voltages around the loop is equal to 0. KCL says that sum of the currents leaving a node is equal to 0. So let's take a look at a circuit. Okay, so I'm going to draw a circuit. I just did. So let's say you've got a current source with 10 amps flowing. We want to know how this current essentially divides between these two resistors. So, intuitively, this current comes in, and some of it goes through R1, some of it goes through R2. So let's label this as I1. Let's label this current as I2. So this is I1, this is I2. And of course, these are going to also drop voltages across these resistors. So we're going to call this V1. We're going to call this guy here V2. So V1 is the voltage across R1. V2 is the voltage across R2. And so we've labeled everything. We have labeled all of our currents. We have labeled all of the voltages. Again, we're interested in finding formulas for all of the voltages and all of the currents that we have here. Now, notice that the number of nodes that we have here, notice that this node and this node and this node, they're all connected. So this whole is one big node there. So it's just one big node there. And then at the bottom here, that also is one big node here again. So we only have 2 nodes, and one of the nodes is the ground there. So sum of the currents leaving the node is equal to 0. So let's apply KCL. So I'm going to look at this top node there, and I'm going to use KCL. So sum of the currents leaving the node is equal to 0. Now the current I1 is leaving the node, so I'm going to say I1. Okay, plus this I2 is also leaving that node, and then this 10 amps is actually entering the node. So when something is entering, we just put a negative in front of it, and that's kind of like 10 amps leaving. So 10 amps is entering is equivalent to minus 10 amps leaving. So we have I1 plus I2 minus 10 is equal to 0. So that's the statement of KVL. So that's our first equation that we can write. Again, we also have, notice that if I take 10 to the other side of the equation, this tells me that I1 plus I2 is equal to 10. which makes sense. It basically says that this 10 amp is going to divide into I1 and I2, so that makes sense. Now let's use Ohm's law. Ohm's law. Okay, according to Ohm's law, we have V1 is equal to I1 R1. And then V2, that's the voltage across R2, is going to be R2 I2. Now, notice that this node is shared between these two resistors, and this node is also shared between these two resistors. When two components are connected at both nodes, we say those elements are in parallel with each other. So I guess I'm going to define that later on, but let me just state it that when we say two components are in parallel with each other, we mean basically that at both ends they share a node. So these two, they are in parallel because on top they share a node, and on the bottom they share a node. So we say these elements are in parallel with each other. And when elements are in parallel with each other, essentially the potential difference is going to be the same. So V1 and V2 are going to be the same, and they're both equal to each other. And that's because R1 and R2 are in parallel. So when elements are in parallel with each other, their voltage is the same. Let's go back to the voltage divider rule that we just discussed. And if you remember, these two elements, as you can see, they're connected, and we say they're in series with each other. Notice they share essentially one node, and there's no other nodes that are involved here. And so essentially when current flows in this circuit, the same current that flows through R1 is also going to flow through R2 because the current has no other place to go. So these two elements are in series, and they're going to have the same current flowing through them. So when elements are in series, they're going to have essentially, they're going to share the same current. And likewise, when elements are in parallel, they're going to have different currents, but they're going to have the same voltage across them. So V1 and V2 are equal to each other. So from here, setting these two equations equal to each other, we're going to have R1 I1 is equal to R2 I2. So there's a relationship between I2 and I1, and we can actually solve for one of them. So I can actually solve for I2 in terms of R1. So R2 is equal to R1 I1 over R2. So the currents are actually proportional to each other. Now, let's go back to the KCL, and we actually now have a relationship between an I1 and I2. We have another relationship between I1 and I2 here, and so we're going to say plug in KCL. So plug it into KCL, I'm going to write I1. Now for I2, I'm going to use this formula here. So I'm going to use R1 over R2 I1, and this is equal to 10. Let me, instead of using 10, let me just use a general voltage level. So we'll get a so I'll just point out that Vs is equal to 10 to make a correspondence between those two. All right, so now I have a I1 in terms of Vs, so I can calculate for I1. I'm running out of space, so let me move on to the next page. Okay, so we can actually solve for I1 in this circuit here. So we have I1 is equal to 1 plus R1 over R2 is equal to Vs. So therefore, I1 is equal to Vs divided by 1 plus R1 over R2. So let's simplify this. So Vs, so that's going to be R2, and that's going to be R2 plus R1. So that's I1 here. So we have I1. And then finally, I can go back in this equation and find I2 here. So I2 is equal to R1 over R2 times I1, and I1 is equal to Vs times R2 over R2 plus R1. Notice the R2s will cancel each other out, and we are left with Vs times R1 over R2 plus R1. Okay, we have a formula for I1, we have a formula for I2, and we can also calculate V1 and V2, which is basically the same voltage there. And so we're basically finished. We have solved for I1, we have solved for I2, and by multiplying either one by the value of the resistor, we're going to get essentially the same voltage across these two different components. So let's generalize this result here. So for the, this is called the current divider circuit. Current divider circuit. Again, this is a important standard circuit. So I'm going to redraw the circuit again. So we want to see how a current source essentially divides between two resistors, R1 and R2, and the current is flowing in that direction, and we have IS. Oh, I just realized I had made a mistake. I had called this current here previously. I used the symbol of Vs. Well, that's confusing because it is a current. I should have called it IS. So let me correct that over there, and this should be IS. And this should be IS across. Okay. Yeah, so I'll just state the all right, I'll just state the okay, sorry about that. So now we're going to put the correct statement. So I1 flows through R1 and I2 flows through I2, and we have the following result, that I1 is equal to IS, which is the value of the current source, times R2 divided by R1 plus R2. And finally, I2 is equal to IS times R1 over R1 plus R2. So this is how the current divides between the two resistors in a current source. So the current source, current flows. This much of it goes through R1, and this much goes through R2. If you look carefully at these formulas, let me put down the formulas for voltage and the current divider. You will see that there's a similarity between the formulas. In both formulas, we have the value of the source in front. In both formulas, you always divide by sum of the resistors. But in the voltage divider rule, the voltage across resistor 2 appears on top. And for the voltage across R1, R1 appears on top. In a current source, that's not true. It's the other way around. So for I1, it's actually the R2 that appears on top. So the value of I1 actually depends on the other resistor, and the value of I2 depends on the other resistor. So there is that, so there's a lot of similarity between these two formulas. But anyway, here's the general formula, and you got to realize for the current source the things are sort of crisscrossed. So I1 depends on R2 and I2 depends on R1. There, whereas in the voltage divider rule, the voltage across R2 depends on R2. So this one is, again, it's the other way around. This is called the current divider circuit. It's basically a circuit that shows how the current in a current source divides between two elements. Again, let's take a look at extreme cases. If, for example, if R2 is much, much bigger than R1, from this formula, we can see that I1 is almost equal to IS. So if R2 is really big, all of the current is going to flow through the other resistor. So current likes to flow in the smaller resistor. And that makes sense because if you think about it, a resistor resists the flow of electricity. So this current wants to divide. Which way is it going to go? Well, it's going to go in the resistor that provides the least resistance. So most of it is going to go through the smaller resistor. And so anyway, for the voltage divider, it's the other way around. Most of the voltage appears in the bigger resistor. In the current version, for the current supply version, it's the other way around. The current likes to flow in the smallest resistor. So that's the extreme case. Since I mentioned the smallest resistor or the largest resistor, let's introduce a term short or short circuit. A short circuit in a circuit essentially means that resistor essentially goes to zero, or the resistor is actually equal to zero. So if you have a circuit and between two nodes there's a piece of wire, we say that there's a short circuit in that wire there. So a short circuit essentially means between two nodes you essentially have no resistance. And an open circuit means that the resistance essentially is infinity across those terminals. So an open circuit is usually denoted by essentially a broken terminal. So let's say if you have, let's take a look at a circuit. Okay, take a look at this circuit. You have a couple of resistors here. You have a couple of resistors here. Notice that between these two nodes, there's a piece of wire. So you have a short circuit there. And here you have essentially an open circuit there. Notice that when you have an open circuit, you no longer have a closed circuit. You no longer have a closed loop. So if you think about it, if there's a current starts flowing in here, current doesn't flow, doesn't fall out in general from the terminals. So essentially, if you have an open circuit, there's not going to be any current flow in a circuit here. So in this circuit, there's no current flow. So in an open circuit, the implication in an open circuit is that the current in that circuit is zero. There's no current flow. In a short circuit, if you think about it, there's definitely going to be a current flowing through this short circuit. But if you think about it, if there's a resistance of zero between these two nodes, then according to Ohm's law, V is going to be 0 times I. So in a short circuit, we're going to have the voltage, which is equal to 0. So these are important terminologies that you need to be familiar with. We're going to see them again later on: open circuit, short circuit. Of course, the term short circuit is also commonly used in the English language, in many different ways. Usually short circuits cause fires, and they can cause problems, and so therefore it's used commonly in the English language. But anyway, in circuit terminology, short circuit essentially means that the resistance between two nodes is equal to 0. Open circuit means that there's infinite resistance between the two nodes. In an open circuit, there's no current flow, and in a short circuit, there is current flow, but the voltage is equal to 0. Again, in an open circuit, there's no current flow, but there's going to be a potential difference here. So between these two open terminals, there's going to be a voltage, but there's no current. Here, there is current, but the voltage is equal to 0. Now, by the way, the reason we mentioned that sometimes when you have short circuits, you have fires and etc. and all that, that follows from Ohm's law, because I is equal to V over R. Notice that as R goes to 0 and V stays constant, I will go to infinity. So if you have a short circuit, essentially you're going to have an infinite flow of electricity flowing, current flowing through that particular branch. That extremely large current is going to turn into heat, and it's going to burn and cause fires. Of course, for safety reasons, we generally have fuses that will usually cut the electricity and open the circuit and prevent fires and disasters. In fact, I'm sure most of you are familiar with fuses. That's what they are. They're there to prevent a short circuit producing an infinitely large current. So that large current will essentially cause the fuse to blow out, and once the fuse blows out, creates an open circuit and will stop the flow of electricity.